So if we can recall, and I think this was one of the questions that came up, is that the typical flow sheet for your free milling ores consists of comminution, gravity concentration, flotation, leaching, some form of purification or concentration stage, recovery, and then finally refining. So typically, if you have a complex ore, that pretreatment stage then comes before leaching. And that is then to liberate your gold minerals that may be locked up by refractory minerals so that you can then, improve your recovery. Also, it is important to note that not all of these processes will be applicable to all circuits. So you might find that you've got a circuit that just goes for comminution, gravity concentration, and then that's it. You might find others that have all of these and others that maybe do not have oxidative pretreatment. It all depends on your ore mineralogy. Okay, so I'm going to go into the different types of methods that are then used for beneficiation. So I'm going to be starting off with comminution, which then consists of crushing and grinding. So crushing typically produces a coarse ore, and the equipment that is used for that includes jaw crushers, cone crushers, impact crushers, and gyratory crushers. Then grinding, that is applied for the liberation of your fine-grained gold particles. So you are then grinding finer than what your crushers can ultimately then produce. So mills are typically used for grinding, and that can be anything from your semi-autogenous mills, and ball mills, depending on what your textural analysis dictated. So the sizing and design of your crushers and mills, that is then dependent on your textural analysis, as we had discussed in the previous parts of the presentation, where you establish the work index of your ore. You also determine the specific energy that is required in order to efficiently break your ore to the optimum size. Okay, then gravity concentration is applied to recover gold and gold-associated heavy minerals. So the important considerations for your gravity concentration circuit include the gold grain size and its distribution within your stream, the degree of liberation and the particle shape. You need to also then consider your density differences of minerals within the stream and their hydrophobicity. So typical equipment that is used includes your shaking tables, drums can be used, spirals can be used, panning bowls can be used, as well as Falcon and Nelson concentrators. Okay, then flotation is a concentration stage that removes undesired material from your stream. So for example, if you have a stream where your main minerals are gold oxides, then flotation will remove your sulfides and your carbonaceous contaminants in the floats. It is then up to you when you are doing the design of the plant, whether you're going to then treat those floats or discard them. Then if your main minerals within your stream are gold sulfides or arsenides or tellurides, then flotation is then going to concentrate your stream in the floats, because your main mineral is maybe a telluride or arsenide. And then this will then leave your contaminants behind in the flotation tanks. So the important considerations to consider includes the size of the gold grains, the composition of your stream, and the selection of your activators and depressants that are used in your flotation circuit. So the types of equipment that are generally used is your agitation tanks and your flotation columns. Then onto gold amalgamation, which is a simple method of recovering gold. And this was basically a method that was used during ancient times. So this method is better suited for gold recovery in small scale alluvial mining operations. However, it is also a popular method that is used by illegal miners. So the process is performed by contacting mercury with the gold-bearing ore to produce an amalgam. The amalgam is then distilled or it is heated to recover the gold. So this method is typically suited for alluvial gold deposits or material that has already been processed previously, but still has some concentration of free gold within it. Amalgamation, however, is less used in your big industrial operations, and this is because of the adverse environmental impacts that mercury has on the environment. So the typical equipment that is then used is your amalgamation cylinder. That is basically where mercury is then mixed with your ore, and then the amalgam retort is used to distill the mercury from your gold. Okay, then on to leaching, which involves the dissolution of gold from a solid particle into the solution phase. So this typically then occurs by chemical reaction where gold cyanide complexes are formed, and these are then readily dissolved into solution. So this whole reaction is governed by the Elsner equation. So the important considerations to include are the particle grind size, your reagent dosage, the presence of complex and refractory minerals within your mineralogy. Then the types of leaching that are typically used are agitated leaching, heap leaching, vat leaching, and intensive leaching. There is also in situ leaching, but I haven't included it for this presentation because that is commonly used for other commodities, not really for gold as such. Okay, agitated leaching. This takes place in tanks where the solids in a slurry are kept in suspension by air or mechanical agitation. So the image on the left shows an example of a Pachuca tank that is air agitated. Then the image on the right shows a mechanically agitated tank that uses rakes at the bottom of a flat-bottomed tank, and that is to keep your solids in suspension. Okay, heap and or dump leaching. This takes place at a designated pad, which is normally sloped, and this is where your ore is stockpiled into a heap. So a pre-conditioned leaching solution is typically sprayed at the top of the heap and allowed to percolate through the ore particles to dissolve gold. Then the pregnant solution then collects at the bottom of the heap and is recovered from there and sent for further processing downstream. Okay. So vat leaching. Vat leaching takes place in a vat, which is normally made using either wood or concrete or steel, where the ore is then immersed into the leaching solution. So this process was basically developed to minimize or avoid channeling and ensure that each surface of the ore is uniformly wetted, if that is a word. There is uniform wetting along all of the surfaces of the ore. And this is sometimes a challenge when it comes to heap leaching. So vat leaching is an older technology and it's not really commonly used in your big industries anymore. And this is due to the high operating and capital costs that were associated with erecting these types of vats. Then we have intensive leaching, and this takes place in a reactor at elevated temperatures and pressures, and this is then to ensure that your dissolution rate is increased. So this type of leaching is commonly used to extract gold from gravity concentrates, for example. So the diagram on the right shows a batch inline reactor, which was developed by Gecko. So essentially, the way it works is that your gold concentrate or whatever ore that you're going to be running through your reactor is added with your reagents. That would typically be lime, cyanide, and perhaps hydrogen peroxide to improve your DO levels, dissolved oxygen levels. These are then added to the reactor where leaching takes place. So the pregnant solution that is generated from the reactor is sent for further processing, maybe to an electrowinning circuit or to a precipitation circuit. And then the solids from there, which are now tailings, are sent to the discard facility. Okay, then concentration and purification is typically done through adsorption. Even thickening and filtration can also be used. So starting off with adsorption, this is achieved using activated carbon or ion exchange resins. And this is done to absorb the gold that is now dissolved in your solution onto the surface of your adsorbent. So this is typically done using a CIP or CIL circuit, or if resin is used, it will be an RIP and an RIL circuit. The dynamic is basically the same. It's just that your resin is typically then designed to selectively absorb the gold. Carbon will absorb a lot of base metals if they are part of your mineralogy as well. Then thickening separates your gold-rich solution from your solid tailings. So the solution is then either sent to a carbon in solution circuit or a resin in solution circuit, or you can then send it straight to a precipitation circuit. Okay, then we have desorption, which is the reverse of your adsorption process. So this is the process where gold is stripped from the surface of the adsorbent into a high-grade gold solution. So this is typically done using elution columns. Okay, so the recovery of gold is done by precipitation or electrowinning. Gold precipitation is done using zinc dust as a precipitating agent, and this is to convert your dissolved gold into a solid precipitate. Then electrowinning involves the deposition of your gold from the solution onto your cathode plates. So the important thing to consider is the type of mineral that you are going to be refining, security requirements around the handling of your high-grade concentrate material, the product quality, and the purity of the gold that you are producing. So then depending on the product specifications, in the case of electrowinning, you can then opt to sell the cathodes as they are, or you can then further treat your material and generate a gold sludge that is then smelted to produce your bullion. Then similarly for your precipitation, you can then opt to sell your precipitate as a concentrate, or that concentrate can then be smelted to produce your bullion bars. Okay, to the refining of gold, this is done by electrorefining, where the bullion bar is placed as your anode in an electrolytic circuit. So your anode, which is now your bullion bar, is dissolved into an electrolyte solution, while at the same time, your dissolved gold is recovered selectively onto your cathode plate in a purer form. And this then leaves your impurities behind in the solution. And this is how your refineries generate gold that is at a purity of 99.99%. Okay, so finally, in conclusion, the gold beneficiation process selection is influenced by a number of factors, which we went through in part 1 of today's presentation. Similarly, it is very, very important for you to understand the type of gold ore that you're going to be treating. So a thorough ore mineralogy assessment needs to be done. A thorough technology test and pilot plant test work needs to be done. There needs to be proper test work that has been done, proper sampling that has been done for you to get the best and the most accurate measurement of your recovery. So lastly, I just wanted to add that at VBCOM, we do have a team of geologists, miners, and process engineers who are able to assist with any of your gold-related queries. So I might not typically be a specialist in something, but there might be somebody else in the team who then has a better grasp of that knowledge. So we are able to facilitate test work programs and conduct studies and designs for processing and mining operations as well. Okay, then I just want to end off here with a list of references that I had used in compiling this presentation, and I would recommend